Let's move on to the next one. So what is close to finite rank? Close to finite rank is compact operators. So then the next logical step is to have a Fredholm alternative for compact operators, like in theorem 744. Again, we have a subset in the complex plane and an analytic map, lambda maps to B lambda, where now the operators are called B. And we assume each B lambda is compact for each lambda in G. Then again, we have one of the two alternatives. Either I minus B lambda inverse exists for no lambda, or it exists for almost every lambda except a discrete set S. And so in this case, the map lambda maps to I minus F lambda inverse is analytic when it exists. And if lambda is in S, then the equation F lambda phi equals phi has a finite dimensional family of solutions. So here the proof is really the same as before. I use a spectral representation of B lambda, and then I approximate B lambda by considering finite sums. Okay, so B lambda can be written as the sum of the little bij's Cj. Sum I is 1 to infinity, and then I cut it off and I say sum is I is 1 to n, and I use the previous result for the finite rank operators. So I leave it at that. I'm not going to go into any more details. But here's a great example. Let's apply this to the spectrum of an integral operator. So compute the spectrum of the map U maps to Ku, which is the integral from 0 to 1, e to the minus gamma x minus y, u of y dy. I always wanted to be able to compute the spectrum of an integral operator. This is a very classical thing. So I, for example, would have gone to classes where we do lots of integral operators. But the modern way of doing functional analysis basically ignores, or maybe does not do so much on integral operators. But you saw in my course, I use it as a standard example all the time. So here it is again, with a very specific kernel, e to the minus gamma x minus y. Domain of definition is L2 plus. So meaning, here's the little plus. So I take L2 functions which are larger or equal to 0. Hey, what's going on? Yeah. Okay, so the kernel e to the minus gamma x minus y is L2 integrable, right? You can just integrate it from 0 to 1. In both variables x and y, you get something finite. So the kernel is in L2, so this makes the operator be compact. It's also called a Hilbert-Schmidt operator. So, which means it has a discrete spectrum of eigenvalues with a possible limit point at 0. Right? This is the previous result. So we can have a discrete set S with eigenvalues. So we can look for eigenvalues, which means we solve an eigenvalue equation. Ku is lambda u, so write it out, integral 0, 1, e to the minus gamma x minus y u of y dy is lambda ux. Now we multiply this by the kernel again, e to the minus gamma z minus x, and we integrate over y. No, sorry, we integrate over x. Okay, so then here is the factor, and here on the other side is the factor. Lambda just comes out, and then we integrate this whole thing on x. But just by definition here on the right, this term here will be equal to lambda u. So this is equal to lambda u again. So then together we get a lambda square u. On the other hand, though, we can directly compute this. We can multiply this exponential with this exponential. And what do we get? We get e to the minus gamma z plus gamma x minus gamma x plus gamma y. So the gamma x terms cancel. So now I'm here. And then we can write this to be the integral from 0 to 1. Here's an inequality. Here, this is too much. E to the minus gamma z minus y u of y dy. And then the x integral here, this integral will integrate just to 1. And now this here is equal to lambda uz. So, making this long story short, we just get lambda square uz equals lambda uz. Oh, beautiful. So then lambda square must be lambda, which means lambda is 0 or lambda is 1. So we find two possible eigenvalues, but we are not sure if they are really eigenvalues, so we need to check that. So if lambda is 0, right here, then we have that the integral from 0 to 1 e to the minus gamma x minus y u of y dy equals 0 times u of x, so equals 0. But now we know that u is non-negative, so which means, and the exponential is also non-negative, of course, so it means u is 0 almost everywhere in 0, 1. But now we work in L2, so in L2 being 0 almost everywhere means u is 0, right? So these are measurable functions. They are only representatives of a class of functions which differ by a set of measure 0. So if it's 0 almost everywhere, it is considered to be the 0 function. And so it is not an eigenfunction. Then lambda is 0 is not an eigenvalue. If lambda is equal to 1, like here, then we need to solve the integral operator equals 1 times u. Okay, and then, yeah, how to do this? In this case, you just take a educated guess. You just try something. So let me show what you try on the next page. So we try this guy here. U equals e to the minus gamma x. So we just sub it in. Instead of u, we sub in e to the minus gamma x. We can factor out a minus gamma x. So we sub in u of y. So we sub in e to the minus gamma y. Let me get my pen again. So here. But they cancel each other, so they integrate to 1. So we keep e to the minus gamma x, which was original u of x. So here we found an eigenfunction. So this means, finally, the spectrum of this operator here is just one value, the value equal to 1. We are lucky because earlier we showed that the spectrum cannot be empty. So this one is not empty. It just has 1 point. Okay, as a final remark here, there is something famous, the Krein-Rootman theorem. My goodness, there's a big spelling. Tuman, so Rootman theorem, which says that lambda 1 has finite multiplicity and a unique positive eigenfunction e to the minus gamma. Oh, it has multiplicity 1, sorry, and a unique positive eigenfunction. Finite multiplicity we know already from the Freedom alternative, but the positive eigenfunction we haven't. Yeah, Krein-Rootman is a bit more involved, so we are not covering that here. All right, so that's my attempt in online teaching, the first lecture here. The spectral theorem, the spectral Freedom alternative I want to do in the next lecture. We'll just see what continues here. And Hilbert-Schmidt in the next lecture, and then I have a little summary which I also do in the next lecture. Let me know if you have questions. I'm available via email and whatever kind of media I can find to answer questions. See you next time.